this week's Tuesday seminar. I'm delighted to introduce our speaker this week, who's Valentina Grazian, who's going to tell us about exotic fusion systems.
Thank you, Paula, and I'd like to thank all the organizers of this great program for the chance of being here and also to present my work today. I will talk about exotic fusion systems, and the new results I present today are joint work with Chris Parker. The plan for the talk is this one. First, I'll give you a brief introduction to the theory of fusion systems. Then I'll focus on the exotic ones. I'll give you some examples of exotic fusion systems, and then I'll give you new results that we hope will help us in understanding exotic fusion systems at all primes. So let's start from some motivations. Why do we care about fusion systems? Fusion systems are the modern way to study the p-local structure of a finite group. If G is a finite group, P is a prime dividing the order of G, then a p-local subgroup of G is any subgroup of the four normalizer in G of P, where P is a p-subgroup of G. And it turns out that if we know some properties of the p-local subgroups of a group, actually we can deduce properties of the group G. This is the so-called p-local approach, and it has application in several areas of mathematics and algebra. For instance, in group theory, especially in finite group theory, we can deduce, as I said, properties of finite groups coming from properties of their p-local subgroups, and an example is the proof of the theorem of classification of finite simple groups, where the two local subgroups play an important role. Another example is modular representation theory. We all know nowadays many conjectures are of the kind local to global. So we study the situation locally, p-locally, we get information globally. And then we also have applications to homotopy theory. An example is the Martino-Predi conjecture, that's now a theorem, that roughly speaking relates the p-local structure of groups to the p-completion of their classifying spaces. So it seems important to get a better understanding of p-local structure of finite groups. And as I said, the way to do that nowadays is via the theory of fusion systems. What do we mean by fusion? If we have a finite group G, prime P dividing the order of G, and a Sylow P subgroup S of G, then we say that two subgroups P and Q of S are fused in G if they are conjugate by an element of G. And now we want to look at all the subgroups of the Sylow S and try to understand which one are fused. To do that, we introduce a category, the fusion category of the group G on S. This is a category where the subgroups, the objects are all the subgroups of S, and the morphisms are exactly the restriction maps, the restriction of conjugations by elements of G. So if we take P and Q, two subgroups of S, Hom G, PQ denotes the restriction of conjugation by elements of G that maps P inside Q, that fuses P inside Q. And if we look at the restriction of conjugation from P to itself, we denote this set by odd GP. This is actually a group with composition, and it is isomorphic to the normalizer in G of P, quotient the centralizer in G of P. So studying automorphism group in the fusion category is equivalent to study the p-local subgroups of G. And now we want to do something more. I can tell you, take your favorite P group. Can you tell me how many fusion categories you can get on them, depending on the group G you choose? Sometimes different G give the same fusion category, or sometimes you have different ones. So can you tell me all the possible fusion categories you can get on a P group? To answer this question, we introduce an abstract notion, the one of fusion system. Fusion system F on a P group S is a category again where the objects are as before. They are all the subgroups of S. What are the morphisms this time? We cannot talk about conjugations because we don't have the group G. So what we do, we give a series of axioms that make sure that our morphisms look like conjugations. First of all, we want them to be injective. Then we ask for all restriction of conjugations by element of S to be in our category. So we have S, we can take conjugation by elements in S, and we want these morphisms in the category. And then we ask technical axiom. We want every morphism to be composition of an isomorphism and an inclusion. This is a fusion system on a P group S. And now when I gave you the definition of a fusion category of a group G, I asked for S to be a Sylow P subgroup. I could have given the definition without this requirement, but I added it because Sylow P subgroups have a very nice properties. And we want to keep properties also in this general setting. So we add some axioms, and when these axioms are satisfied, we say that the fusion system is saturated. And saturated fusion systems are really the object that people are interested in studying. So from now on, anytime I say fusion system, what I really mean is saturated fusion system. And going back, if we start from a group G, we take a Sylow, we build the fusion category, this is a saturated fusion system on S. The interesting thing is that sometimes you can start from a P group, you can select morphisms between subgroups that satisfies all your axioms, even the saturation axioms, but you cannot find any finite group G containing your P group as a Sylow and realizing the fusion, realizing the maps you have selected. When this happens, we say that the saturated fusion system is exotic. So again, exotic means something works fine, it really looks like an action of a group by conjugation, but there is no group G finite realizing it. So I'll keep the definition of exotic on top, and exotic fusion systems are somehow an open problem in the area. For the prime P equal 2, actually there's only one known infinite family of exotic fusion systems, the so-called Benson-Solomon systems. But when P is odd, we have many examples of exotic fusion systems. And the situation here seems a bit chaotic. The examples seem unrelated, and it's not clear how these exotic fusion systems arise at odd primes. This led Oliver to pose these questions that lead to a research direction, try to understand exotic fusion systems at odd primes, try to understand why they arise, how they arise, and if not all of them, at least a large class of them. And the results I'll talk about today are part of a project that aims at answering, at least partially, this question. So to try to understand exotic fusion system when the prime P is odd. Before moving on, I want to show you an example. So when we work with fusion system, the first thing you want to do is to fix the prime. I chose P equals 7. And then you choose your favorite 7 group. This time I chose a Sylow 7 subgroup of the group G, choose 7. The first thing you do, you try to familiarize with the group. So S here is a group of order 7 to the 6. Now let's look at the lower central series. I write gamma 2 of S for the derived subgroup of S, gamma I of S for the commutator subgroup of gamma I minus 1 of S with S for I greater or equal than 3. This gives me all the members of the lower central series of S. And now we have a group of order 7 to the 6, so surely gamma 6 is trivial. In this specific group, actually gamma 6 is the first term of the lower central series that is trivial. In other words, the P group S has class 5, so it has maximal nilpotency class. So the lower central series is as large as it can be. And in maximal class P groups, the lower central series corresponds to the upper central series. So gamma 5 is the center, gamma 4 is the second center, and so on. Also, in my picture, so when you see a dot, there is a subgroup, and you look from the bottom up. So the center of S has order P, as S7 in this case. The second center has order 7 square and contains the center, and so on. Now, in a maximal class P group, the members of the lower central series are all the normal subgroups that are not maximal. So what we see in this picture are all the normal subgroups of S except the maximal subgroups. So let's look at the maximal subgroups now. First of all, we can define a subgroup gamma 1 of S as the centralizer in S of gamma 2 over gamma 4. So this is a 7 square. Gamma 1 is one of the so-called two-step centralizers because it centralizes a two-step in the lower central series. Now we said it's a 7 square, is not centralized by S because by definition gamma 2 commutate S is gamma 3. And this 7 square is normal in S. Therefore gamma 1 is a maximal subgroup of S. It has index 7 in S. And it turns out in maximal class P groups, what I'm saying is general for maximal class P groups, that this group gamma 1 is the two-step centralizer of every P square, so also gamma 3 over gamma 5, except possibly the last step. So the last two step is the second center of S. Sometimes this is also equal to gamma 1 of S, the centralizer of this quotient. Sometimes it is not. In this particular 7 group, it is not. So we have another maximal subgroup, I denoted by C. This is the centralizer in S of the second center. So we have these two maximal subgroups in S that are characteristic in S. What else? Well, the commutator subgroup of S has index 7 square, so the number of maximal subgroups is P plus 1, so 8. So there are 6 more. Well, the 6 maximal subgroups that are left, they all have maximal nilpotency class. I just write one of them for simplicity, but there are 6 of them, all of maximal nilpotency class. And now the one you see in the picture are all the normal subgroups of S. One last thing, inside the maximal subgroups that have maximal nilpotency class, we can see a 7 square that is self-centralizing. So I write 7 times 7 to mean that this is a direct product of two cyclic group of order 7. And this subgroup P of S is self-centralizing in S. It will be important later on. Okay, so this is about the subgroups of S. Let's do some fusion. So we need to pick a group G containing S as a Sylow. The easiest case, we can take G as S itself. So then what are the fusion maps? Conjugations by elements in S. So all we see are inner automorphisms of S, nothing more. And well, if we look at the subgroups, all the normal subgroups are only fused to themselves. We are not moving them, conjugating by S. All the subgroups that are not normal are fused to something else. For example, this P is going to be fused to some PG, staying inside M, of course, and so on. So this P is fused around inside M, and this happens for every maximal subgroup M. Not very interesting. So let's change the group G. Now, by definition, we took S as a Sylow G27. So let's look at G27. What are the fusion these times? So restriction of conjugation maps to subgroups. The inner of S are always there. So we always have conjugation by elements of S. This time, the normalizer in G of S is bigger than just the inner automorphisms. And in fact, if we take the normalizer, we quotient out the centralizer, we quotient out also S, because we already take care of the inner. What we get in the fusion system, in the fusion category we are studying, is a 6 times 6. So a direct product to cyclic group of orders. So we have this automorphism of S acting on the group. Of course, once again, the members of the lower central series, they are characteristic in S, so they will be fixed. They will be fused only to themselves. Same story for gamma 1 and C, but the other subgroups, the non-characteristic ones, are moved around. There is something more. We can look at the normalizer in G27 of the maximal group C. Now, gamma 3 is the fratini of C, and actually we see there's a GL27 action in this 7 square that's faithful in the sense that gamma 2 is moved around. So gamma 2 is conjugated to all the other maximal subgroups of C. So these maps that we see here, they could have come from automorphism of S. But then we look at the action, no, there are maps that move gamma 2, that is characteristic in S. So they are different maps. We need to add them to the list if we want to describe all the fusion maps. We cannot consider them as restrictions coming from the normalizer in G of S because we are moving gamma 2. So we need them in the list. And we also need in the list the maps acting on gamma 1. In here, we are fixing gamma 5, that's also the center of gamma 1. I didn't tell you before, but in this scenario, gamma 1 is extra special. But we have some maps, again, a GL27 that moves around, for example, gamma 3. So these are not maps coming from C, these are not maps coming from S, so they are new maps. We need to add them to our list. And these are all the fusion maps, in the sense that the fusion category of G27 on these groups is completely determined by the automorphism of S, C times 6, the automorphism of C, GL27 with the inner, automorphism of gamma 1, GL27 with the inner automorphism. This means that every fusion map you see is a composition of restrictions of these maps. So maps coming from S, from gamma 1, or from C. We can go larger. We can take the monster group. S is a Sylow of the monster group. So what are the fusions these times? This time we see the inner of S. They're always there. We same again, normalizing G of S. Again, this is 6 times 6, as before. As before, we have a GL27 acting on C. Again, the normalizer of gamma 1 plays a role. It's a different group this time. It's not a GL27, it's a different group. Still, this normalizer is important. Moreover, P plays a role now. Now, if we look at the normalizer in the monster of P, it contains an SL27 acting on P as P is a natural model for it. So in particular, the center of S is moved around. It's fused to all maximal subgroups of P. And now we play the same game. So we have this morphism that fuses and moves in particular the center of S. Where does it come from? Well, P is not containing gamma 1, it's not containing C, so the morphism cannot be restrictions coming from gamma 1 and C. It cannot come from S because we are moving the center. So they are different maps. They are not restriction of the first 4 bullet points. We need to add them. And that's it. So the fusion of the monster of this group is given by these automorphism groups. S, gamma 1, C, and also the SL27 coming from P. And you can build more fusion categories on these same groups. Also, Parker, together with Semeraro, in classifying fusion systems on Sylows of G2P, they determine exotic fusion systems when P is 7. So on this group, there are several exotic fusion systems. And in all but one, there is this SL2P. So this P, this 7 square, plays an important role in the description of the fusion system. Let's keep this in mind because we'll come back to that later on. Okay, so what we have seen with this example is that we can build different fusion categories on the same group. We can build exotic fusion systems, and in order to describe the fusion system, we just need the automorphism groups of some subgroups. We don't need to look at them all. We just need to focus on some subgroups, and then we know that all the restriction and composition of this map will give me all the map in the fusion system. That's a theorem. That's the Alperin-Goldschmidt fusion theorem that says that a saturated fusion system is completely determined by the automorphism group of S and of certain subgroups that are called essential for this reason. So in the previous example, we saw in the fusion of G27, we have gamma 1 and C essential. In the fusion of the monster, we have gamma 1, C, and P essential. Now, what's the right definition of an essential subgroup? So an essential subgroup, E of S, is a proper subgroup such that the centralizer in S of Q is in Q whenever Q is conjugate in the fusion system to E. So whenever there's a map that fuses E to Q, I want the centralizer in S of Q to be contained in Q. Then I want the order of the normalizer in S of E to be greater or equal than the order of the normalizer in S of Q. Again, whenever Q is a subgroup fused to E. And then we have an important property on the automorphism group that we see in the fusion system. We want the outer automorphism group in the fusion, this is the quotient of the automorphism group by the inner, to have a strongly p-embedded subgroup. This means there's a subgroup H, such that P divides the order of H, but P does not divide the order of H intersection A to the G, whenever we take G in the outer automorphism group, but not in H. Okay, let's see some consequences. So the first property tells us in particular that E is self-centralizing. If we take Q equal E, we get centralizer in S of E is contained in E. In particular, if our P group S is abelian, then no proper subgroup is self-centralizing, so we don't see any essential. So when you choose your P group to be abelian, the fusion is not very interesting. It's that if you have a group G, the normalizer in G of S, or in general, is the automorphism group of S. The second property, together with the third, tells us that the automorphism group of an essential in the fusion system has a restricted structure. Now let's think again about the examples. What groups did we see? We saw GL27, SL27. These are groups that have a strongly 7 embedded subgroup. And this is true for every P, GL2P, SL2P. So we don't have all possible candidates for the automorphism of an essential. We need to select the subgroups of the automorphism group of E that have a strongly p-embedded subgroup. Okay, and now the Alperin-Gauchmi fusion theorem gives us a recipe to classify fusion systems. It's telling us that the first step, you look at your P group, you look at the subgroups, and try to decide what are the candidates for being essential. Then try to understand what their automorphism group can be. You saw in the example gamma 1 and a different automorphism group in G27 and in the monster. So you need to find also the candidates for automorphism groups. Once you have that, combine them. Just find all the right combinations that make sense. And in this way, you'll find all saturated fusion systems. When you have the list of all the fusion systems, now decide, do they come from a group or are they exotic? So it's time to go back to exotic fusion systems at all problems. What are some examples? What are some non-exotic fusion systems? First example of top out primes were presented by Ruiz and Vira in 2004. They constructed 3 distinct exotic fusion systems on a 7 group of order 7 to the 3 and exponent p, an extra special group of order 7 to the 3 and exponent 7. That was shocking at the time, because that's a very small group, and people didn't really expect these exotic fusion systems to appear, and well, there were 3 different on a 7 to the 3. That's where the story started. People started asking themselves, okay, what are these exotic, why they appear, can we determine them all, or can we find some behavior they have? So the first attempt was to build examples. And Ruiz and Birol, again, with Diaz 2 years later, they classified the fusion system on section rank 2 groups, again for B odd, and they found new exotics for P equal 3. They found infinite families of exotic fusion systems for P equal 3 for specific families of S having sectional rank 2. And from the first two examples, you might think, okay, there are exotic only for certain primes. Well, no. Parker, together with Stroop, built an infinite family of exotic fusion systems for all primes P greater or equal than 5 on a specific class of groups of order P to the P minus 1. These are groups having a maximal subgroup that is extra special, so of order P to the P minus 2. Okay, so we have lots of exotics for all primes. And Parker with Semeraro, 2017, as I mentioned before, they studied the fusion system on a Sylow G2P, and as I said, they found exotic when P is 7. In my PhD thesis, I classified the fusion systems on groups of section rank 3 for p greater or equal than 5. In doing that, I uncovered a new exotic fusion system, and that's one defined on a group of order 7 to the 5, and its nickname in magma is small group 7 to the 5, 37. What kind of group is that? Think about the Sylow of G27. Remember, we had two characteristic maximal subgroups, and then we had this M maximal subgroup of maximal nilpotency class. Well, it is one of those M. So it's a maximal subgroup of the Sylow G27. Okay, so we have this bunch of examples, and they seem unrelated. At the first look, one say, okay, what do they have in common? How can we expect to have a global picture of exotic fusion systems? Well, they have something in common. The P groups that are in this list, they all have maximal nilpotency class. So there is a link among them. So probably the situation is not as chaotic as one might expect. All these examples are on P groups of maximal nilpotency class. And now I need to add other examples to this list. There are lots of examples of exotic fusion system on P groups having a maximal subgroup that is abelian. These groups don't have maximal nilpotency class in general. And the exotic here were found by Oliver, Craven, Semeraro, and Ruiz. However, if we add the assumption that the center of S has order P, then again, we are in a P group of maximal nilpotency class. And I'll explain it better later on, but the essential subgroups we see in the exotic, in this class of group in general, they have a structure that is similar to what we see in the maximal nilpotency class groups. So it's not a completely different case. It's somehow related to fusion system on maximal nilpotency class groups. So the goal of the slide was to convince you that it makes sense to try to study fusion system on maximal class groups. It's not just yet another class of P groups we study, but if we can get a full classification, then first we recover all the known examples, and maybe we'll find a good way to link them. We'll find a reason why they appear all in maximal class P groups, and then in a way we'll get an answer to Oliver's question. Study a large class of exotic fusion systems. Okay, so this is our goal now. Classify fusion system on P groups on maximal nilpotency class. And again, I mean saturated fusion systems. And remember, I told you, how do you classify fusion systems? Select your class of P groups. Done. P groups on maximal nilpotency class. Next step, find the essential. Find the candidates for being essential. Well, I'm very proud of this theorem because Chris and I did it. We found the essentials. And this theorem was completed, I think, a week and a half ago, so we need to thank the program for that. And here it is. So if P is an odd prime, S is a P group of maximal nilpotency class, F is a saturated fusion system, then the candidates for essentials are the group gamma 1 of S, the centralizer in S of the second center, or some small groups. A direct product of P with a P, cyclic of order P with a cyclic of order P, or an extra special group of order P to the 3 and exponent P. And these are the groups that I call pearls. That's it. So these are the essentials that we saw in the Sylow of G27. So we know this is the right list. And also, the Sylow G27 didn't have the extra special pearl, but there are examples where we know there is the extra special. So this is the right list. And this result is somehow surprising because first, there is no classification of P groups of maximal nilpotency class for P greater or equal than 7. So we don't have a classification of the p-groups. Anyway, we were able, with fusion techniques, to determine the only candidates for essential subgroups. The other thing is that we don't have any assumption on the sectional rank of the p-group. In other classification, we use the fact that we knew the sectional rank of the group. Here, we don't have any assumption of that. Furthermore, we don't have any assumption on the fusion system besides it being saturated. We are not asking for it to be simple, reduced. We are not asking for OP of F to be trivial. We are just asking for F to be saturated. So that's somehow surprising that we could describe the whole list of essentials. And actually, we know a bit more than that. For instance, we know that in the automorphism group of the pairs, we always see an SL2P. So when we have, for example, the P squared, the action is exactly the one I show you in G27, like the center is moving around. And the extra special pair, we will have the center of S fixed and the second center moved around. We can say even more. So I told you before, in a maximal class P groups, the first two groups in the list, sometimes they are the same group, sometimes they are distinct. When they are distinct, and the centralizer of the second center is actually essential, then we are in a Sylow or G2P, and the fusion then are known. So somehow, if we want to do the classification, we can ignore the case when they are distinct and this is essential. We can assume we have only gamma 1 and pairs, because as soon as it is essential, we end up in G2P and then we know what happens in there. Okay, let's focus for a moment on pairs. So I repeat here, what is a pair is an essential that is either a p squared or an extra special of order p to the 3. So I mentioned before during my example that when there are the exotics in all but one, we see the pair. We see this SL2P acting, and we see that in our list of maximal class, the candidates, there are these pairs. So maybe the pairs are the one inducing exoticity. Maybe it's not really about maximal class P groups, it's this SL2P acting on a non-normal subgroup that makes things weird for a group. And then actually, a consequence of a theorem of Suzuki is that whenever we have a pair, we are in a maximal class P group. So maybe that's it. Maybe the fact is not about the class of maximal class P groups, but it's because they are induced by pairs. And then one might ask, are the two things equivalent? In the sense, we know we have pairs implies maximal class P group. Is it true that whenever we have a maximal class P group, we have pairs? Well, you can answer this question. The answer is no. I'll show you the example of G27. There were not pairs when we look at the fusion category G27 on its Sylow. There were pairs for the monster, but not for G27. But now we have an answer to this question. What was a speculation last summer is now a theorem that G2P is the only exception, in the sense that whenever we have a maximal class P group, and here we need to add the assumption OP of F is 1, this means OP of F is the largest subgroup of S that's normalized by all the fusion maps. So if I assume this to be trivial, then either there are pairs or we end up in G2P. So again, since we know the fusions on G2P, we can assume we always have pairs. How do we deduce this theorem from our main theorem? So I told you the essentials are gamma 1, centralizer of the second center, and pairs. And I need essentials to satisfy OP of F is equal 1. If I don't have essential, then S is normalized by all the fusion maps. So I need some essentials. Suppose there are no pairs. We are left with two, gamma 1 and C. Now I told you before, if there is C, we automatically end up in G2P. Then there is only gamma 1. But then gamma 1 is OP of F, and we have a contradiction. So we cannot have only one essential that is not pairs, so we need gamma 1 and C, and so we end up in G2P again. So it's very easy to deduce this theorem now, having the main theorem. And that's the power of knowing the essentials. You can make lots of deduction when you know the right list. that you need to study. Another thing, another way to look at pearls. I somehow already mentioned it, but the abelian pearls look like the center of S that has order P extended by a P, and the extra special pearls look like the second center of S that has order P squared extended by a P. And now remember, in the list of exotic fusion systems, we have the one on P groups with the maximal abelian subgroup. And I told you, this group don't have maximal nilpotency class. However, Oliver proved that in this case, so when S has a unique maximal abelian subgroup A, then the candidates for F essential are A itself or groups of this form. You see, they look like pearls. So as soon as we know that the center of S has order P, then this is an abelian pearl, and it follows automatically that this is an extra special pearl. So in any case, if the center of S is not of order P, the structure of the essentials is similar. And let's look at our main theorem. We have a maximal subgroup here, and we have two maximal subgroups. Now, if gamma 1 is abelian, in particular, it also centralizes the second center. So this corresponds to A, and then we have the pearls. So the situation is not completely different. And maybe, if once we complete the discussion on fusion system containing pearls, we might want to generalize and try to attack the problem of fusion system when we have essentials of this type. And then we'll also recover Oliver's example. That's an ambitious statement, but maybe that's the way to go. And also, Oliver says, if this subgroup is trivial, this is the one normalized by all the fusions, and A is not essential, then we are in a maximal class group. So again, these are pearls. So you see, also in this example of exotic, we are not too far from what we are studying. Okay, I want to conclude giving you the flavor of the proof and telling you a bit of the tools we are using to prove this mean theorem. So the first thing we do, we take a minimal counterexample. So we take a fusion system F where these are not the essentials. So there is some essential that is not in this list. By minimal, we mean first on the size of the P group and then on the number of morphisms we see. So in particular, we end up in P greater or equal than 5 because the three groups are unclassified and they are known and things work well in that situation. So we are P greater or equal than 5 and there is a weakness, an essential E that is not in this list. Now, the first thing we can do, we can assume there are no pearls in our minimal counterexample because there's a way to remove pearls and still get a saturated fusion system. So that's a bit the problem with fusion system. When you remove something or you quotient, you certainly can get a fusion system, but you might lose saturation, and you want to keep saturation. When there's a way to remove pearls and get a smaller saturated fusion system. So in our minimal counterexample, F does not have pearls. And now, that's an easy lemma that says that the essentials either are pearls or are inside gamma 1 or inside the centralizer on the second cell. When these two groups are distinct, we can get rid of the essentials that are only inside this group. So we can assume E is inside gamma 1 of S, and we can assume all essentials that we see are inside gamma 1 of S, and since E is not in the list, it's properly contained there. In particular, gamma 1 of S is not abelian. Remember, essentials are self-centralizing, so gamma 1 of S is not abelian. And we can also prove that gamma 1 of S is not extra special. So we are not in the Sylow G2P, for instance. Looking at the structure of P group of maximal nilpotency class, this is enough to prove that the outer automorphism group of S, this is the automorphism group quotient by the inner, this has order P minus 1. So not in any fusion coupling, really, the full outer automorphism group has order P minus 1. And now in particular, in my fusion system, this is a subgroup of it, so it will have order at most P minus 1, and actually its order divides P minus 1. So we have some restrictions on the morphism, the automorphism we see in S. Now, the first hard step is to reduce us to the case OP of F is 1. So there is no subgroup that is fixed by all the morphisms. And to do that, we need to use classification of simple groups with p elements acting quadratically. So here we use the classification of simple groups. Yeah, and it's not an easy step, but we can reduce this. And now, so this is what we know. We know OP of F is 1. We have this weakness inside gamma 1 of S, and we know we don't have too many morphisms coming from S. Now, this is the trick. This is the very hard part. It took us some time to come out with the right T. We can take a T proper inside gamma 1 and non-trivial such that. So the first line, this is the normalizer in f of t is not contained in a normalizer in f of gamma 1 of S. Roughly speaking, the automorphism we see acting in T, they don't come from automorphisms of gamma 1 or from S. So when you work with fusion system, you're always doing this. You look at your group, you see some morphisms, where do they come from? Either we are in an essential, so they come from the essential itself, or they need to come from above as restrictions. Where can they come from, knowing what they fix, what they move, the same kind of reasoning we did during the example. So here we say there is an essential not in gamma 1. So there are some morphisms in this essential that don't come from gamma 1 or from S. So E satisfies the first property. But we are not working with E because when we go into subfusion system or we take quotient, E might not be essential anymore, so we lose kind of the induction step. But then if we take T, we are not asking for T to be essential, we are just asking that there are some automorphisms of T that don't come from gamma 1. So they need to come from something else. Somehow we are saying that T is contained in another essential that is not gamma 1. And then we take some maximality assumption. So first we want the normalizer in S of T to be maximal, and then the size of T to be maximal. So we want somehow a big normalizer that pushes T to be small, but then we take T the largest of the small one. Okay, now that we work with this T, we have the two cases. T is F-centric. The centralizer in S of every conjugate of T is contained in this conjugate. So this is F-centric, is the first property of essential subgroups. So if T is F-centric, we reach a contradiction of the existence of this T using the CGT theorem, so heavy machinery here. We need to invoke this theorem to get rid of the case T is F-centric. And the other case then is T not F-centric. And again, we need now to work with some big results on modules for group with a cyclic Sylow. Now, what are the group here? Here is the automorphism group, the one that gives me some these morphisms that I don't know where they come from. So there's an automorphism group or some essential, and I can assume this as a cyclic Sylow, and then it needs to act on some module, and I can use results about this action to get a contradiction. And in particular, we use phase theorem, just one example of the results we used, and we can get rid of this case. So T does not exist, so E does not exist, so the essentials are the one in our list. And this concludes the proof, and it also concludes my talk. Thank you very much.
Any questions or comments?
Yes.
What did you mean by p elements acting quadratically? What does that mean?
So we mean that, so we have our P group, we look at its normalizer, there is some P acting like conjugation, that's a P element, and we want quadratic action.
What does
So
quadratic action mean?
Okay. So if you have a module V, and then you have P element X, you want V, commutate X to be trivial. So when you act twice.
Okay.
Means Jordan blocks have length of those two.
Yes. Thanks.
Yeah.
More of a comment than a question. I learned from your talk that about 35 years ago I found a pearl in the monster.
So, has anybody tried to compute the cohomology of any of these exotic examples?
Actually, I don't know about that. Yeah,
That seems like an interesting project to me.
yeah, it would be interesting to see that as well.
All right, well, let's thank Valentina again.